Hello everyone, our topic for today is liquid chromatography mass spectrometry. Liquid chromatography. It's a method of physical separation in which the components of a liquid mixture are distributed between two immiscible phases, stationary and mobile. The practice of LC can be divided into five categories: adsorption chromatography, partition chromatography, ion exchange chromatography, size exclusion chromatography, affinity chromatography. The most widely used variant in the reverse phase RB mode of the partition chromatography technique, which makes use of an unpolar phase and a polar mobile phase. In common applications, the mobile phase is a mixture of water and other polar solvents, methanol, isopropanol, and acetonitrile, and the stationary matrix is prepared by attacking long chain alkyl groups to the external and internal surfaces of irregularly or spherically shaped 5 micrometers diameter porous silica particles. In HPLC, typically 20 microliters of the sample of interest are injected into the mobile phase stream, delivered by a high pressure pump. The mobile phase containing the analytes permeates through the stationary phase bed in a definite direction. The components of the mixture are separated depending on their chemical affinity with the mobile and stationary phases. The liquid solvent mobile phase is delivered under high pressure up to 400 bar into a packed column containing the stationary phase. The high pressure is necessary to achieve a constant flow rate for reproducible chromatography experiments, depending on the partitioning between the mobile and stationary phases. The components of the sample will flow out of the column at different times. The column is the most important component of the LC system and is designed to withstand the high pressure of the liquid. Conventional LC columns are 100 to 300 millimeters long with outer diameter of 6.4 millimeters, quarter inch, and internal diameter of 3 to 4.6 millimeters. High-performance liquid chromatography is a technique in analytical chemistry used to separate and identify each component in a mixture, as well as other forms of chromatography in HPLC. There is a mobile phase which forced by a pump to pass through the system, and there is a stationary phase called a column, which located an oven where the temperature can be controlled. The sample can be automatically injected into a HPLC system by the use of HPLC autosampler or can be manually introduced into the injector using a syringe. There is also a detector attached to the HPLC system which measures the analytes after its separation in the column. The pump forces the mobile phase through the column and then the detector under high pressures. In the HPLC system, a vacuum pump and a degausseur are connected to the pump and used to remove dissolved gases from the solvent. The pump drives each solvent to the mixing chamber, where mixing takes place under higher pressures. HPLC analysis commonly uses isocratic or gradient elution. In isocratic mode, the mobile phase composition remains constant throughout the procedure, whereas in gradient mode, the mobile phase composition is changed during the separation process. Sample introduction can be accomplished in various ways. The simplest method is to use an injection valve in the load position. The high pressure eluting solvent flows to the column directly. The loop is loaded at the atmospheric pressure from a syringe via the needle port. Excess sample exits the loop via vent port. After loop, The separation is based on differential partitioning of the sample components between the mobile and stationary phases. The component which has more affinity to the mobile phase, consequently less affinity to the stationary phase, travels faster and exudes out faster. And the component with high affinity to the stationary phase and less affinity to the mobile phase travels slower and eluted later. This separation can be carried out according to which type of HPLC used. There are two main types of HPLC: reverse phase HPLC and normal phase. Reversed phase has a non-polar stationary phase and moderately polar mobile phase. One common stationary phase is a silica, which has been modified by attaching a straight-chain alkyl group to its surface, such as the etadiazyl group C18 or the octyl group C8. In this case, the more hydrophobic the analytes are, the more retained they will be on the stationary phase. The more the polar they are, the more they will be preferred the mobile phase. Then normal phase chromatography, the stationary phase is polar and mobile phase is non-polar. This method separates analytes based on their affinity for a polar stationary surface, such as silica. In this case, the more polar the analytes are, the more retained they will be on stationary phase. The more hydrophobic they are, the more they will prefer the mobile phase. As compounds elute from the column, they interact with the detector. Different types of detectors can be used, such as the UV, this detector which is showing an absorption spectrum in the ultraviolet or visible region. For UV detection, a deuterium discharge lamp as a light source is used, and for components detection. We can also find entrance slit, lens prism or diffraction grazing, X-slit, flow cell, and a detector for absorption measurements. Light from the lamp is shown onto the prism and dispersed according to the wavelength. When the measurement is performed with a specific wavelength, the angle of the prism is adjusted so that the light of this wave can shine on the flow cell as the compound elute from the column. They enter the flow cell where the bonding and non-bonding electrons of these compounds can absorb every energy in the form of the UV or visible light. The manner in which the final data is displayed and based on the computer in software. The number of the peaks present can indicate how many components are in the mixture. Usually, the x-axis of the HPLC chromatogram shows the amount of time taken for the analytes to pass through the column and reach the detector. Typically, the y-axis or the area of the peak is a reflection of the amount of specific analyte that is present. Liquid chromatography (LC) is a separation technique that separates the components of a sample based on the differences in their affinity or retention strengths for the stationary phase and the mobile phase. This separation is illustrated in the following figure 1, where the components in the sample are separated in a LC column. Sample in purple is injected into the LC column and gets separated into two analyte bands, red and blue, and gets eluted from the column. Detectors for LC systems. Even separation by LC, the components can be detected using optical properties such as ultraviolet visible, UV visible, fluorescence, refractive index, evaporative light scattering, or electrical conductivity, based on the analyte's properties. Figure 2 shows the various detectors for LC. When the analyte passed through the detector, a change, increase or decrease in the optical property will be observed and recorded. Different types of HPLC detectors. 1. UV visible detector. A. Fixed wavelength. B. Variable wavelength. C. Diode array detector. 2. Mass detector. 3. Fluorescence detector. 4. Refractive index detector. A. Deflection detector. B. Refractive detector. 5. Electrochemical detector. These columns have smaller internal diameters, allow for a more efficient separation, and handle liquid flows under 1 ml per minute, the conventional flow rate. In order to improve separation efficiency and peak resolution, ultra-performance liquid chromatography (UHPLC) can be used instead of HPLC. This LC variant uses columns baked with smaller silica particles, 1.7 micrometer diameter, and requires higher operating pressures in the range of 310,000 to 775,000 torr, 6,000 to 15,000 psi, 400 to 1034 bar. Mass spectrometry is an analytical technique that measures the mass to charge ratio, m over z, of charged particles ions. Although there are many different kinds of mass spectrometers, all of them make use of electric or magnetic fields to manipulate the motion of ions produced from an analyte of interest and determine their m over z. The basic components of a mass spectrometer are the ion source, the mass analyzer, the detector, and the data and vacuum systems. The ion source is where the components of sample introduced in a MS system are ionized by means of electron beams, photon beams, UV lights, laser beams, or corona discharge. In the case of electrospray ionization, the ion source moves ions that exist in liquid solution into the gas phase. Liquid chromatography, mass spectrometry, LC, and MS. We start with the nebulizer. And then the droplets of mobile phase and sample turns to ions and going into sampling capillary. Then to the skimmer. Octuple ion guide. And then by lenses, ions get into quadruple mass filter. And then to the beam shaper. By entrance lens, they go to collision cell. And then by X lens and beam shaper turns to quadruple mass filter. then ions going to the detector and the conversion diode. Ions be separated to the secondary diode and electron multiplier. And then we measure the relation between abundance and the ratio m over z. We start that ions going in the ionization chamber and vacuum pump. And then acceleration plates going from the magnetic field and then going into the detector to display and measure mass spectrograph. While liquid chromatography separates mixtures with multiple components, mass spectrometry provides spectral information that may help to identify or confirm the suspected identity of each separated component. MS is not only sensitive but provides selective detection, relieving the need for complete chromatographic separation. Liquid chromatography mass spectrometry (LC-MS) is an analytical chemistry technique that combines the physical separation capabilities of liquid chromatography or HPLC with the mass analysis capabilities of mass spectrometry. Coupled chromatography (MS) systems are popular in chemical analysis because the individual capabilities of each technique are enhanced synergistically. For applications involving LC-MS, the length of chromatography columns can be shorter, 30 to 50 millimeters, with 3 to 5 micrometer diameter baking particles. In addition to the conventional model, other LC columns are the narrow bore, micro bore, microcapillary, and nano LC models. Briefly, with the coupling of LC with MS, the mass spectra obtained from these measurements provide molecular mass and structure information for eluted components, which therefore LC-MS combine the outstanding separation resolution of LC with the excellent qualitative capabilities of MS. The ion source converts and fragments the neutral sample molecules into gas phase ions that are sent to the mass analyzer, while the mass analyzer applies the electric and magnetic fields to sort the ions by their masses. The detector measures and amplifies the ion current to calculate the abundances of each mass resolved ion in order to generate a mass spectrum that a human eye can easily recognize. The data system records, processes, stores, and displays data in a computer. The LC chromatogram in red shows an example of a typical chromatogram obtained using these optical detectors. LC coupled with optical detection offers great quantitative accuracy for analytes that can be chromatographically resolved, where a detected peak comprises only a single component. However, achieving required resolution is challenging for complex samples where multiple components elute approximately at the same time. A mass spectrum plots the relative ion intensities against the m over z values, and a series of mass spectra are generated at each time point in blue. This information indicates the concentration level of ions that have a given mass and is extremely valuable for the unique identification of molecules, also known as a qualitative analysis. Moreover, MS provides added specificity and sensitivity and the convenience of multi-component analysis. A typical LC chromatogram is the red one, and a LCMS mass chromatogram and mass spectrum the blue one. Instrumentation. This is a diagram of an LCMS system. The first is HPLC device, where solvents is a mobile phase, then samples, multiple component mixtures, move through HPLC column to LCMS interface ion source, then mass spectrometer to detection, and finally mass spectrum analysis. In addition to the liquid chromatography and the mass spectrometry devices, an LCMS system contains an interface that efficiently transfers the separated components from the LC column into the MS ion source. The interface is necessary because the LC and MS devices are fundamentally incompatible, while the mobile phase in a LC system is a pressurized liquid. The MS analyzers commonly operate under high vacuum. Thus, it is not possible to directly pump the elute from the LC column into the MS source. Overall, the interface is a mechanically simple part of the LCMS system that transfers the maximum amount of analyte, removes a significant portion of the mobile phase used in LC, and preserves the chemical identity of the chromatography products, chemically inert. As a requirement, the interface shouldn't interfere with the ionizing efficiency and vacuum conditions of the MS system. Nowadays, most extensively applied LC-MS interfaces are based on atmospheric pressure ionization (API). Strategies like electrospray ionization (ESI), atmospheric pressure chemical ionization (ABCI), and atmospheric pressure photoionization (ABBI). LCMS system contains of HPLC system and mass spectrometer. Instrumental analysis. For a LCMS system, the instrumentation comprises of 1. LC unit, 2. An interface between the LC and MS, 3. An ion source that ionizes samples, such as ABI unit. 4. An ion guide, an electrostatic lens that efficiently introduces the generated ions into the MS. 5. A mass analyzer unit that separates the ions based on their mass to charge m over z. 6. A detector unit that detects the separated ions. The basic components of a LC unit consist of 1. Auto sampler injects the samples. 2. Column for separation of sample. 3. Detector for the analysis of the separated components in a sample. 4. Pump delivers the mobile phase at a required flow rate. Comparison of LCMS and GCMS techniques. 1. Apart from LCMS, there are various ionization techniques and analytical instruments for chemical analysis, such as inductively coupled plasma (MS), ICP MS, matrix assisted laser desorption ionization (MALDI MS), and electron ionization (EI) with gas chromatography (MS), GCMS. MS was first introduced and used as a detector for GC systems in late 1960s, and their advantages have been widely recognized. 2. GC separates volatile compounds in a column where the mobile phase is an inert gas and the stationary phase is either a baked column or a coated liquid. The compounds are retained and separated based on their polarity, volatility, boiling point, and their interaction with the stationary phase. Compounds undergo a hard ionization, electron ionization, to form gaseous ions and are further analyzed by MS. 3. GCMS technologies provide a very effective means for separating, qualifying, and quantifying substances, but its applicability is limited to gases or volatile compounds with relatively low molecular mass and samples with high thermal stability. Differences between HPLC and GC. Gas chromatography and high performance liquid chromatography are separation techniques used in obtaining specific elements from an analyte based on the compounds in the analyte distribution between the two phases, mobile phase and stationary phase. 1. Mobile phase. One of the major differences between these two methods is the difference in their mobile phases, which eventually determines where each technique is used. As the name suggests, gas chromatography uses gases as its mobile phase, with the stationary phase either being liquid or solid. On the other hand, high-performance liquid chromatography uses a liquid as its mobile phase and a solid as its stationary phase in analysis. 2. Nature of analyte. Compared to high-performance liquid chromatography, gas chromatography analyzes samples that are either volatile or semi-volatile. Thus, it will analyze only few samples since volatile compounds are fewer than non-volatile samples, which the HPLC analyzes. Inadvertently, HPLC analyzes samples that are only liquid in nature. 3. Instrumentation. Both these methods use chromatography columns, but there is a differentiation in their sizes. The gas chromatography uses columns which are long and thick, usually 10 to 30 meters in length, as compared to the chromatography column which is shorter and thin, basically being 5 to 25 centimeters in length. For detection, after chromatography is done on the analyte, the composition of the element has been done. This calls for detection methods that are stringent to get the perfect sample type and volume. Each analytical technique has its own method of sample detection. For gas chromatography, two types of detectors are the most widely used. The flame ionization detector, FED, that is only used for detection of hydrocarbons, and the thermal conducting detector, TCD, which is universal and detects any substance. In the case of high-performance liquid chromatography, the only method used is via an ultraviolet spectrometric detector, which uses the principle of absorption and transmittance to detect the different types of samples. In spectrometry, a sample is placed between a source of light and a photometric reader. The amount of light passing through the sample is recorded as a photons by a computer detector. Different samples have different absorbance rates. 5. Cost. Finally, the cost of each technique is a determining factor. The gas chromatography technique is less costly compared to the HPLC system that utilizes a lot of equipment, including high pressure pumps to increase its accuracy and shortens time required for analysis of the sample. For LCMS provides broad applicability for an extensive range of substances, polar and nonpolar, and offers high selectivity. LCMS was only made possible in mid-1970s with the introduction of atmospheric pressure ionization. With the use of ABI, the LC elutionate, vaporizes, and ionizes to form gaseous ions, which are subsequently introduced into the MC. ABI is a type of soft ionization technique, and examples include atmospheric pressure, photoionization ABBI, atmospheric pressure chemical ionization ABCI, and the commonly used electrospray ionization ESI. One of the advantages of LCMS is its broad applicability to a wide range of compounds. 5. Once the sample is dissolved in a mobile phase, LCMS can analyze even the least volatile or thermally unstable compounds that are difficult to analyze using GCMS. Applications. The coupling of MS with LC systems is attractive because liquid chromatography can separate delicate and complex natural mixtures, which chemical composition needs to be well established, such as biological fluids, environmental samples, and drugs. Further, LCMS has applications in volatile explosive residue analysis. Nowadays, LCMS has become one of the most widely used chemical analysis techniques because more than 85% of natural chemical compounds are polar and thermally labile, and GCMS cannot process these samples. As an example, HPLC-MS is regarded as the leading analytical technique for proteometics and pharmaceutical laboratories. Other important applications of LCMS include the analysis of food, pesticides, and plant phenols. In the environmental field, LCMS is widely utilized for the qualitative and quantitative determination of known pollutants, such as pesticides, bacteria, pharmaceuticals, and personal care products, and the trace level emerging contaminants. In LCMS instruments, it's used for detection of pesticides in essential oils and liquids. We have mobile phase A is ammonium formate and formic acid in water, and mobile phase B is ammonium formate and formic acid in methanol. And then we're gonna make injection of sample in LCMS. Each column has a different matrix, particle size, pore size, length, and width to allow for different kinds of testing. For pesticides, we use biphenyl column. This column is perfect to separate pesticides. And then sample will move to source in a vacuum system. So the sample moves from the needle to interface with 5 BA and then to 0.1 BA, and then we'll move to Q1 with in Q2 it's called the collision cell and it has magnetic and electric energy, and then we move to Q3, then to the detector. In which molecules have a unique fragmentation. Then the mass is measured. For example, if a pesticide parent molecule has a mass of 142 m over z and a daughter molecule of 93. For example, if a pesticide parent molecule has a mass of 142 m over z and a daughter molecule of 93 m over z, this information will be used in the multiple reaction monitoring table to specify what instruments need to look for. If the daughter molecule is recorded with that mass, it means that the pesticide is present in the oil sample. If the daughter molecule mass isn't, the parent molecule isn't the pesticide and is not present in the sample. LCMS instruments, liquid chromatography mass spectrometry.